All right, so today we're going to completely switch gears and talk about something that seems kind of unrelated to what we've been talking about. In organic chemistry, we have focused so much on names and reactions and synthesis and all that sort of stuff that we really haven't talked a lot about what's called spectroscopy. And spectroscopy is a very valuable tool in organic chemistry. You might remember way back when in Gen Chem 1, when we performed that experiment with the colorimeter where we measured the amount of copper sulfate, that beautiful blue compound in solution. Now, every spectroscopy experiment is laid out basically the same. Okay, you're always going to start off with some sort of light source. Okay, depending upon what type of spectroscopy you're doing, that will determine what your light source is. Okay, that light source ultimately is going to pass through your sample, which is either in a cuvette or a test tube or something like that. And some of that light's going to be absorbed by the sample and some of it's not. The light that's not absorbed by the sample is going to be picked up by a detector, which is going to send a signal to a computer. Okay, and for the purposes of the experiment we did back in Chem 101, all we were really interested in was the absorbance of the light of the sample. Now again, in that experiment we were dealing with light in the visible wavelength region. That's not going to be the case for most organic compounds when we're trying to study them because, well, most of them are not, don't have any color to them. So, in organic chemistry, the type of spectroscopy that we're going to use is not visible light spectroscopy, but rather IR spectroscopy. Okay, and in IR spectroscopy, our light source is going to be an IR light source, essentially a laser. Okay, so this is going to be light that has longer wavelengths than visible light. Okay. Now, usually that means wavelengths in the order of centimeters up to meters or so. Okay, and what we're able to do is we're able to select out certain wavelengths. I'm going to call this a wavelength selector. Okay, now this is a little bit more complicated for IR than it is for other types of spectroscopy. But just know that we have the ability to measure how much light is being absorbed at a given wavelength. Okay, and then again, this can go through our sample. Which then, the light that's not being absorbed is picked up by a detector and sent to a computer. All right. Well, why do we do this? Well, we do this because it turns out that IR light interacts with organic compounds in a way that causes the bonds to stretch. So, for example, if you consider a molecule of water, okay, we know that bonds are kind of like springs. Okay, so they're constantly oscillating, so they're kind of getting shorter and longer, but they have this kind of this average distance between the two atoms. Okay, but if I were to shine IR light of a particular wavelength onto this water molecule, what that's going to do is it's going to cause one of these OH bonds to start oscillating. Okay, so back and forth. So we have this bond that's going to be stretching back and forth. And that means the light's being absorbed, so that light does not make its way to the detector. Okay, there's all different types of motions that can be induced by IR light, depending upon what the nature of the bond is, whether it's an OH bond or a CH bond or an NH bond. Okay, they all absorb at different frequencies. Okay, so since different types of bonds absorb at different frequencies, we can look at the spectrum produced when we shine a whole bunch of different wavelengths of IR light onto a sample. We can see which ones are being absorbed. So usually this is going to be a plot of transmittance, okay, which is a measure of how much light actually makes it through to the detector. Okay, if we have 100% transmittance, that means all the light has made its way to the detector and none has been absorbed. If we have 0% transmittance, that means that all of the light's being absorbed and nothing's made its way to the detector. Okay, and then we have frequency. On the horizontal axis. Okay, and that's usually measured in wave numbers. Okay, which the actual unit is inverse centimeters. Now, you don't need to worry too much about that, except that the range for a typical experiment goes from 4,000 wave numbers down to about 800 wave numbers. Okay, and what we find is that if we put a sample into the IR spectrometer and we scan across all these different frequencies, what we wind up with is a pattern that looks something like this. Okay, now that's just a random pattern that I made up. But what we find is that these low points here represent where light is being absorbed. Okay, and each one of those absorptions is due to a certain type of bond being present. So what this allows us to do is to look at these absorptions and predict what bonds are present in the compound that we're studying. Now, there are some people out there who can look at one of these things and they can look at every little blip on there and they can make a prediction about the actual structure of a compound. That's not what's expected of you here in this class. We're just going to try to pull what evidence we can from the IR spectrum of a compound. Okay, so that's the whole basis here. So what we want to do is we want to look at the spectrum, we want to identify where the absorptions are, and then we're going to correlate those to the type of bond that they correspond to. And that's what I'm going to show you in the next video.